Well, I looked at your quizzes. They looked great. You can kind of check on some of my annotations. And so if there's something there that you see that doesn't look right, you can write me a note, right? Or ask me about it. But I thought for the most part, those looked really good. We're going to finish up 11, 9, and then 9 and 10 for sure, and maybe a little bit of 11, 11. And then do one more small quiz about the same size as the one you did. And then we have the final and you're done. So the quiz will be pencil paper like the last one. So I'll just put it out there. In fact, it'll look just like 11-1. It'll be 11-2. And you can download it, write on it electronically, or with pencil, scan it back in and give it back to me. I'm thinking maybe we'll be far enough on Wednesday that I can give it to you on Wednesday. Otherwise, I'll give it to you on Friday and you can turn it in on Monday or something like that. Okay, and if there's anything else now, as we're getting down to the end, you got to let me know right away. So if you run into a problem with WebAssign, or you're trying to figure something out, or you got some questions about the grading scale or anything, let me know right away so we can get back to you in case it, you know, so that we don't run into the end of the semester. So anything bothering you administratively before we get going? Okay, well, then here's the game. The game is I give you a function and you try to find a power series that is going to be equal, and by equals, I'm going to do equals, right? Equal to it for at least a chunk of the function, for a little piece of the function, an interval of convergence, if you will. The two should agree, right? And the more terms that we add to our power series, the better they agree. In fact, if we write a rigorous proof that if we do the dot, 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 meaning if we keep adding terms forever, then the two functions would be exactly the same over that interval. Now, the best case scenario is that the interval of convergence is all real numbers, right? It works everywhere. Okay, the two just look more and more like each other. And then if we add infinitely many terms, or as we approach a large number of terms, the two functions should look exactly the same every place. Worst case scenario is that they only agree at one point. Okay, and so all of these power series are always going to converge when x is 0, because that you plug in 0 into all the x's and you just get the constant term. So that might be the best we can do. The interval of convergence could be just that one point, right? The constant term, and that's, or x equals 0 and agree at the constant term. And that wouldn't be particularly useful. So we don't really, you know, it's not interesting because it wouldn't be, it's just not interesting. So we want it to agree at least over some small interval. For lots of these power series, we get a radius of convergence of 1, and generally it's centered. A lot of them are centered at x equals 0. So we're going to go from -1 to +1, right? And over that interval, the two functions are going to agree. Now, we can take our function and do a translation. We can shift it over so that the two functions agree still on a radius of 1, but maybe they are maybe it's centered around x equals 2. So then the functions would agree from 1 to 3. Okay, and sometimes the radius is bigger than 1, but for the most part, it's either going to be only at 0 on an interval, right, around some point, and generally that's around 0, or it's going to agree everywhere, which is kind of the best case scenario. And so, but our goal is to see if we can figure out, is there a power series representation of the function? And if so, then tell us some details about it. Like tell us where does it, you know, where does it agree? What is the radius of convergence, or what's the interval of convergence? Now the trick to these, and there's a real trick, and it's a cumulative sort of trick. The way that we start finding these is that we try to make the new ones look like ones we already know. Okay, so to do that, you actually have to know some, otherwise you're in bad shape. So I'm going to say that we know at least one at this point, right? So we know this one. We should definitely know this one. 1 over 1 minus x. It's a pretty easy one to know because I'm pretty sure it's just the straight up power series where all the coefficients, right, all the coefficients are equal to 1. And so we've proved this like 2 different ways. Come on, focus, camera. My camera's having trouble this morning. Try zooming it in a little bit. Hang on. Okay, get that out of there. If I zoom in a little, it'll help. Whoops, zoom out a little, it'll help. Wiggle it, it'll help. I don't know what's going on here. Well, it doesn't want to behave today. There, yeah, it really doesn't want to behave today. Okay, well, a tiny bit blurry. I'll just keep talking. Maybe it'll find itself. So we proved this a couple of ways. 1, we just did the long division. And 2, we recognize this as a geometric series, right? We proved that all the geometric series converge, and we figured out what the sum would be. Okay, so now you can write it in expanded form. And when you do the dot, dot, this is nice because you can see sort of what's going on. But then the dot, dot, dot leaves you wondering, well, I wonder what the rest of the terms are. I think I see the pattern, but it hasn't been explicitly defined. So there are some benefits to writing it in summation notation as well. I don't know what's going on with my camera. Okay. Oh, I see. Well, maybe I don't see. Okay, well, we can write it in summation form as well. We can say it's the sum, right? N equals 0 to infinity of x to the nth power. Okay, and notice here that we're starting at 0 because when I say x to the 0, I get 1, and so I get my first term. So now my first term isn't when n equals 0. This is weird, right? So there's a little bit of it being off here. Do we have internet problems this morning? Are you on somewhere? Yeah, I don't know if we're, I think it's just focusing, but it seems to be lagging a little too. Okay. Okay, so now the question is, can we get other ones? And so the next one that we got was this one. We said 1 plus x would be a good one to get. How do I get that one? And the answer is, well, I don't know, maybe we could substitute, right, a negative x in for this x. Okay, and if you want to use u, you certainly can. You can let x be a negative u. And if you do, then you'd get 1 minus a minus u, which is 1 plus u. Hey, this is looking good. And then everywhere else that you see an x, you're going to put in your negative u, and you're going to get a new power series. And I think this one is going to look something like this. It's going to be the same thing, but it's going to alternate. And so in summation notation, we'd say n equals 0 to infinity minus 1 to the n, x to the nth power. Okay, so now we know 2 of them. Now, while you're writing these down, it's probably a good idea to say, when is this true, right? When are they equal? So you could look at the graph, and we notice that they were equal, right, between -1 and 1. So we'd say the absolute value of x is less than 1. So the absolute value of x is less than 1. So why don't we write down, whether or not we formally prove this as the interval of convergence, or if we just kind of look at it or just get it out of the book, we should probably be, if we're memorizing these, we should memorize what it's equal to and when it's equal, right? So we should be writing those down as well. Okay, so now the question is, how do I get new ones? And the answer is you just kind of keep playing this game, right? You try to, if you want to make a new one from an old one, then you could just substitute something in for this x right here. So we could say, you know, let x be u squared. I usually I usually let x be x squared, right? Which is kind of weird, right? I mean, I probably put in an x squared everywhere I see an x. And that's because math types just like using x for everything, right? So this is a different x from that x. If that's bothering you, then we could rewrite the whole thing in terms of u. And we could say, let x be u squared. And now everywhere I put a u squared, and then I get a new power series, right? For, what do we get? 1 over 1 plus u squared, which would be 1 minus u squared. And then I've got to square my x, so I get u to the 4th. And then I got to cube my x, so I get u to the 6th. And then I've got to go u to the 8th, dot, dot, dot. And in summation notation, n equals 0 to infinity. I've got minus 1 to the nth power. And now in for my x, I'm going to put my u. So I got u squared to the n, power to power u multiplied. I get u to the 2n. And then I'm going to put u in for here. And I'm going to say the absolute value of u squared is less than 1. Okay, and it turns out that this is true when this is true, which means my interval of convergence is still minus 1 to 1. And now everything's written in terms of u. So if you like x's instead, then you can put an x back where the u is and rewrite the whole thing. Okay, so now we've got 3. We've got this one and this one and this one. Yeah, we're doing pretty good. So you just keep going with this game. And hopefully you had a chance to play it a little bit over the last couple of days on the homework. But now what we want to do is sort of go backwards. Instead of starting with the series and then substituting something to make a new one, now what I want to do is I want to intentionally build one. In other words, I want to make this one. How do I get 1 over x plus 2? Okay, so the trick to this is to try to make this expression look like one that you already know. And we only know 3 of them so far. We maybe know a few more from the homework. Okay, but basically we know 3 of them. So the question is, how do I make this, okay, look like one of these? And the answer is, I don't know, algebra. We could start by doing this. Since the addition is commutative, right? We can switch it around. And that's good because that's looking a little bit more like this. Now what we could do is, look, this is 1 plus x. This is 2 plus x. I got to get this 2 out of here. So what I'd like to do is factor out the 2. So to factor out the 2, maybe I'm going to need a 2. I'm going to need a 2 in here. So I'm going to rewrite this like this. Because 2 over 2 is 1, and 1 times x is x, so this still looks legal. And now there's a 2 here that I can factor out. So I'm going to factor this 2 and this 2 out. Here it goes. And I'm going to get 1 over 2 times 1 plus x over 2. Sorry about the focus. Seems to be working some of the time. Okay, so this is starting to look a lot like 1 plus something. In fact, it looks a lot like this one right here, except that I've plugged in an x over 2 instead of plugging in an x. Now there's an extra half in the front, but think about how that works. If it's 1/2 times, so I can rewrite it like this, 1/2 times 1 over 1 plus x over 2 squared. Then if I did half times the series, what I would do up here is I would say half times a half times a half times a half times a half. There'd be a half in every term. And of course, I could factor it out. Okay, so it would go out to the front. All right, so let's see how we get this now. This, I'm going to claim, is the same as our series up above, except I've plugged in x over 2. So I'm going to say that's the same as as 1/2 times, right, 1 minus the x over 2 plus the x over 2 squared minus the x over 2 cubed, right, plus dot, dot, dot. Now it's a little weird because of course we have a half, right? We have a half factored out of a dot, dot, dot. And so somewhere along the lines, we're going to have to prove that the distributive property works over an infinite series. But I think that's believable. So now in summation notation, what do we have? We've got 1/2 times the sum, n equals 0 to infinity. We've got the alternating, so that's the -1 to the n. And then instead of x to the n, right, we have x over 2 to the nth power. And that's it. Katie, what do you got?
I was just confused about a little bit of steps back when you said you went from x over 2 to x over 2 squared.
Where? Oh, I probably screwed it. Oh, I screwed it up. That's why. Because I was looking at this one, yeah.
Yeah.
And so then I got a little ahead of myself here. So this isn't right, but I think everything else is probably right, yeah?
Yep. Okay, that makes more sense. I was like, wait, how did you do that?
Yeah, sorry about that. Factor out the 2, and then this one does look like this one now, yeah? So when I substituted in, I think I substituted into the correct one. Oh, you can't quite see it. There. Right? I wrote the wrong thing here, but I did substitute into the correct formula up here, I think. Right?
Yeah, you did.
Okay. Sorry about that.
No, you're good. Thank you.
Okay. So then I would say, this is it. Here's our formula. We're done. We've got a power series. So what I'm saying is that this should agree with this. And when should it agree? Whenever we put in x over 2 is less than 1. Okay, so when's that happen? That's when the absolute value of 2 is just 2. So I can put that here. That means the absolute value of x is less than 2. So my interval of convergence is going to agree all the way from -2 to 2 now. So we should go look at it, make sure that things are right. And then if I had done something worse than just writing it down wrong and catching it, or making an error and then making it back again, this would be where you'd catch your error, right? You'd go take a look. So let's go find it. So I'm going to use Desmos because that's what I like to use. And I'm going to say, I wonder what this thing looks like, right? So here is our function. Our function was 1 over, I'll even call it f of x so we can plug in, is 1 over, and if you want to write this as x plus 2, or if you want to write it as 2 plus x, it doesn't matter. And then we say our polynomial, right, is going to be equal to, what did we say, 1/2 the sum, n goes from 0 to something big. What did we use the other day, m?
Yeah, we did.
Okay, we'll keep using m. Of -1 to the n, and then we've got x over 2, right, to the nth power. We're going to add a little slider for m. We're going to start it at 0 and go, I don't know, somewhere big, like 20. And we'll go by ones. Okay, so when m is 0, this thing should agree right here at 0. And it does. Check it out. 1/2 and 1/2. Yeah, so they agree right at this point, which is good. But I'm going to say that our using y equals 1/2 doesn't doesn't really approximate the red curve very well for very long, right? In other words, this keeps going down, this stays flat. There's a big error here, and the error gets bigger and bigger, and the error gets fast, right? It gets big fast. So maybe we should try, instead of a horizontal line, maybe we should try the tangent line. So then we try m equals 1. And now look at this. Now the line is a better approximation for the red curve. And it stays pretty close for a while, right? From say minus a quarter to a quarter, it's approximating pretty well. So since the line does such a good job, why don't we try a quadratic? And then you can see that the quadratic agrees right on the nose here at 0. And then it stays tighter to the red line for longer. So it's a better approximation. And then we try 3, and the cubic goes up, right, and then down. And of course, as it goes down, it's kind of peeling away here. But right along here, it looks really tight. Okay, so then what do? More. And you can see that between -1 and 1, this is really doing a good job. In fact, it's looking like it's doing a good job all the way out to almost 2. And of course, on this side, the asymptote is at -2. And it's agreeing as we go up this way, right? Pretty good, right? Pretty good as I get closer to -2. So I would say that our series, right, is approximating our function really well on the interval -2 to 2. Okay, and if we add more terms, better, right? If we add a lot more terms, here, 200 maybe, 200, right? Then check it out. Boy, oh my goodness, look, that's almost right on over here. And of course, look at how close to 2 we are right down there, and it still agrees pretty well. Except that you saw Desmos laboring there because that's a lot of terms for it to graph. Right? So I'm gonna back it off to 20. Okay, questions? That is the game. The game is I give you a function. Wow, the game is get your computer to focus. Come on, iPad. I do not know what's going on with it. It hasn't caused this much problem for us for weeks. Okay, well, I give you a function, and then you're supposed to give me, right, the series. And the trick is try to make whatever I give you look like, right, one that we already know. So the more you know, the easier this is. But in a way, it's also the harder it is because, hey, we only had 3 that we could turn it into at this point. And as you get a whole bag of them, then there are a lot more choices for what to turn it into, right? So this is kind of a game of just having some experience, right, and playing with it. All right, so let's try one more. Let's try this one, in fact, right here, because I'm going to use some of this. All right, so here's the next one. This is number 2. What if I have x cubed over x plus 2? Then I'm saying, you know what? That looks like it's going to be pretty easy because I already know what 1 over x plus 2 is. Right? 1 over x plus 2 would be, where did I write it down? It's right up here, right? 1/2, right? 1/2, 1 minus x over 2 plus x over 2 squared minus x over 2 cubed plus dot, dot, dot. We good?
Mm-hmm.
So what's the difference then? All I'm doing is multiplying the top by x cubed. So since I'm multiplying every term by x cubed, I wouldn't have to distribute it. I can just leave it on the outside. And my claim is going to be that this is just going to be x over x cubed over 2 times the sum n equals 0 to infinity of my, where did I write it down? -1 to the n x over 2 to the n. Yeah. So if you have an x cubed in the top, you just multiply by it. That part's easy. And that's, I think that should make sense. What are we saying? We're trying to model a polynomial using an infinite polynomial. Well, it's pretty easy to model a polynomial with a polynomial, right? Let's go back over to Desmos and see if I can explain. What if we said, hey, write an infinite series for this, x squared plus 2 plus x plus 1, right? Write this as an infinite series. Well, that shouldn't be too hard, right? Since it's already polynomial. If we add more terms to this, right, I'm thinking that that should still agree pretty well. What if we just say the sum n equals 0 to a big number, right, of x to the n? So how well does it agree, right? And you'd say, wow, that does not agree in so well at all. So how come? Check it out. If I go way back here, where does it agree? It agrees at 1. It agrees at 2. It's right on. Okay. At 3, though, it starts to be a little bit off. But on this interval right in here, right, this interval right in here, it fits really well. So these two aren't equal because the number of terms here keeps going up. But this polynomial is certainly modeled really well by a higher degree polynomial, at least on the interval, right? On the interval that we're interested in, from -1/2 to 1/2. I don't know if that makes sense or not. I guess it begs the question, if you have a polynomial, why would I even model the polynomial with the polynomial? I've already got a polynomial. I'm already good, so just stop, okay? What we want to do is model things that are more complicated, okay? And so let's see if we can try some other ones. And then you just do a bunch of these, okay? And then the question is, and then that's it. That's the game. So you try a few of those. So that takes us, though, to a new idea. And let me get an example. So just in case you want to follow it along in the book rather than making one up, I'm going to actually grab one. Make sure I did all my examples here in my notes. Okay, so that looks pretty good. That all looks pretty good. Interesting. Okay. Let's do this one now. Let's do 1 over 1 minus x all squared. Okay, so now we want to do this one. So I'm saying, okay, great. Here is a new function. And what I want to do is I want to build a power series that agrees with this over as large an interval as I can get it to agree. And so you start looking at that and you start saying, well, go down the list of ones you know and see if there's any way to turn this one, right, to turn this one into one of the ones on our list. So what do we know? We know 1 minus x. We know 1 over 1 plus x. We know 1 over 1 minus x squared. We know 1 over 1 plus x squared, right? So we know all these. I'm feeling like this one doesn't look like any of these. In fact, turning this into this is going to be a problem because I've got the middle term, right? I've got x squared minus 2x plus 1. So with the middle term, right? None of these had middle terms. So I'm like, oh boy, I don't know how to do this. So we're going to need a new strategy, right? A new trick. And so look at the ones that we know and look at the one that we need and see if you can make a connection between the two. A connection that you would only know after taking this class.
Would it have something to do with trig?
It might have something to do with trig, but then you might know it after a trig class.
Wait. Does it have to do with the derivative?
It might have to do with the derivative. In fact, isn't this equal to the derivative of one of these that we know? In fact, it kind of looks like the derivative of this one, doesn't it?
Just, isn't it missing the negative?
I don't know. Take the derivative there and check it. See if there's a minus missing, because I always lose them anyway.
Yeah, it would be missing a negative, I think.
Okay, so let's try this. I'm going to, since it's been a while, right? And maybe I don't have these memorized quite as well as I wanted. I'm going to write this way with the power. So then I'm going to use the power rule. And I'm going to say that's minus 1 times the 1 minus x to the minus 2. But then I look inside and it's not just an x. So then I have to do the chain rule times the derivative of the stuff inside, which is
negative. Oops.
minus 1. So minus and minus, those go away. And the negative exponent means I got 1 over 1 minus x squared.
Never mind.
Sweet. Yeah? I would say, maybe if you want to be able to get all these details right, don't quickly run out and become a computer science major. Okay, because what'll happen is you'll just get used to, I don't have to pay attention to the extra minus sign because I can just stick it in Symbol Lab and it'll tell me the answer. And then you won't pay attention to the details. Yeah? But remember that if you are trying to check this, you could always check and probably should check, especially if you lose minus signs all the time like I do. So go put it in Symbol Lab and see what it is, or graph it on Desmos and see if this function, right, is describing, if this function is describing the slope of this one. But I think we have it right. Do we agree? Okay. So this is equal to the derivative of one of these that we know. But we said that this stuff on the inside was equal to a power series. So what if I just put the power series in there? What did the power series look like? 1 plus x squared plus x cubed plus x to the 4th. Notice that it would be a really good idea to know what this is. Otherwise, this is going to be a really hard step. So there's going to be a premium on sort of memorizing a few of these. Notice that it's also a heck of a lot easier to put the power series in there in expanded form rather than in summation notation. But we could have certainly written it in summation notation as well. Right? So now the question is, and this is a big question, how do I take the derivative of something that goes on and on and on and on and on? And that's the question. Does the derivative of a sum equal the sum of the derivatives? And you say, yep, as long as the sum stops, we prove that, right? That's one of the derivative laws from from long ago, chapter 3, probably about October, yeah? You remember that? You're probably out trick-or-treating, trying to memorize this stuff. Okay, so the question now is, well, what if it just keeps going? Would it be true that I could just take the derivative of this term by term, and that the derivative of this infinite series would be equal to the derivative of each term of my series, and then I could just put a dot, 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 and keep taking derivatives? In other words, what if I wrote this? The derivative of 1 is 0, yeah? The derivative of x is 1. The derivative of x squared is 2x. And then this is 3x squared. And then this is 4x cubed. And then this is the derivative of, you know, the dot, dot, dot. That's kind of weird notation. I don't think anybody uses that. So I'm not sure if this is true or not. Somebody would have to prove it. Meaning that the derivative, right, can be done term by term. And if you have infinitely many terms, then you would just take the derivative of the rest of the terms. Seems kind of reasonable, but it should be maybe something that we want to prove somewhere down the road if we go ahead and use this. But maybe what we should do is, you know, see if this even makes any sense at all. In other words, see if what we get agrees. And if it doesn't tell us anything useful, then probably taking the derivative of this probably doesn't work. But if it gives us an answer that we expected, and it's consistent with what we're doing, then this probably is legal. It's much easier to prove something that's legal than something that's illegal, I suppose, right? In other words, can you really do this, right? And we'll just try it and see if it works or not, which certainly is not a proof, but it does provide some evidence that maybe it is okay. Are you with me on this? Take the derivative term by term. Okay, well, if that's true, look at what we get. We get a new series. Okay, in fact, maybe we should write this in summation notation. Well, maybe we shouldn't. First, let's not write it in summation notation. Let's just put it in, because if it's wrong, I don't want to spend any time messing with it, right? So let's just put it in here and see if it's right or not. So what do we got? We got 1 over 1 minus x quantity squared. Okay, so what's that? That's the red stuff. Yeah, that's the red stuff. There it is right there. Okay, so now we say, I'm thinking that that's going to look a lot like 1 plus 2x plus 3x squared plus 4x cubed. And the question is it? And you're saying, well, not everywhere. It doesn't look like it everywhere, but does it look like it over an interval? I mean, it's looking pretty good right through here, isn't it? I'm kind of thinking that at least from -1/2 to 1/2, this is looking like it matches up pretty good. So then I would say, well, what if I add some more terms? 5x to the 4th. Well, that's fitting even better. Doesn't fit over here. Okay, well, that's fine. But it definitely fits here. In fact, I could imagine that this would fit all the way from -1 to 1 if I added enough terms. So the question is, how do I add more terms? Because I don't want to type them all into Desmos. I want to write this in summation notation. So I can say, go to M and drag my slider. So the next big step is, how do I write this in summation notation? And you say, I don't know, doesn't look that bad. It looks like we've got the sum, right? And N is going to go from, something to something. maybe it'll end up in infinity eventually. And then we could say, well, let's see. If I say x to the n power, I would take care of all the powers, wouldn't I? Because x to the 0 is 1, x to the 1 is x to the first, x to the second's right here, x cubed is right there. But then how do I get this number? That's the coefficient. So how do I get the coefficients? And you say,
I mean, it's looking just like the power rule, right? So it'd be nx to the n minus 1.
It sure would be, although the way I wrote it, I think was this. Right? Because look, if I start at 0 and I plug in 0, I got 1 x to the 0, which is 1. And if I plug in 1, right? If I plug in 1, I get 2 x to the first. And I plug in 2, I get 3x squared. But you're right. Isn't that looking a lot like the power rule, but instead of starting at 0, I start at 1? Are these two things the same? And the answer is yes, I just started in different places. But check this out. Isn't this just the derivative of our formula in the first place?
Mm-hmm.
The only difference is I now start at n equals 1 instead of starting at n equals 0. That has to do with the fact that the derivative of the constant equals 0. Sweet, I think we got it. It begs the question, when does it agree? And I'm just going to tell you, it's going to agree on -1 to 1. It turns out that if a function converges on an interval, then its derivative converges on the same interval. And yes, we would have to prove that, but no, I'm not going to right this second. I am going to look in Desmos and see it though, and say, well, it's looking like our series, right? Our original series converged on -1 to 1. And now I'm thinking that this converges pretty well on -1 to 1. So let's write it down. Sum n equals, you get to choose. Do you want to go from 1 to infinity, or do you want to start at 0? If you start at 1, then you got to write n, then you got to write n plus 1 x to the n, yeah? If you want to start at 1, then you can write n x to the n minus 1. It doesn't like those exponents, remember it? There you go. And I'm thinking m equals 14. Look at that, that's agreeing pretty good. That's agreeing really well, in fact. All the way out, m equals 19. It's agreeing pretty well from -1 to 1. And if we let m get bigger, like say 100 or something, look at how close to -1 and 1 we are, and it's agreeing really well. Katie, question?
Nope.
No, okay. Okay, so what does this all boil down to? What it boils down to is this. We've got a new thing that we can do with our power series, and that is that we can take the derivative of the power series and get a new power series, which is pretty cool. As long as you can handle this derivative of the ... and we're just going to take that on faith for now because it seems to be working okay. Okay, and then we might have to prove it later. So maybe the next question would be when, right? When can we take the derivative? And certainly you should know when a function is differentiable or not. So tell me, when is a function differentiable?
Has to be continuous.
It certainly has to be continuous. And for it to be continuous, what are the conditions?
No holes, no breaks.
Okay, no holes,
No
no breaks,
asymptotes.
no asymptotes, no jumps, right?
Yeah.
Okay, so one of the big things then would be no holes. And by no holes, I mean the function itself would have to exist. So you can't take the derivative of a function that doesn't exist. You can't take the derivative of square root x when x is minus 5, okay, because there's no function over there. So now check out our series. Our series only exists on the interval for which it converges. The rest of the time it goes off to infinity. So what's the derivative of infinity? I don't know, it's not anything. So if you're going to try to take the derivative, then you're only going to be able to take the derivative of a power series on the interval for which the power series exists. So on the interval of convergence. So again, the interval of convergence kind of comes into play. This is only interesting where the series has a value. And that's why we were concerned about convergent series and why we spent like 7 sections or 3 and skipped a few. But that's why there were so many sections on trying to prove where does a series converge. Because if it converges, then there's all kinds of good things we can do with it. And if it doesn't converge, it runs off to infinity. Not really that interesting. Okay, so what about that then? If you could take the derivative of a power series term by term, would it seem reasonable that we could take the integral of a power series term by term? Like this. What if I wanted to do the integral? I'm going to pick a really nice one here if I can, because I can never remember it. Okay. The integral of this one. Minus, right? Now I'm going to claim we still have some issues here. I'm going to claim that it's going to be hard to anti-differentiate a function that doesn't exist. So for sure, this would only work on the interval of convergence. But I'm also worried about this. Because if I'm anti-differentiating, then the dot, dot, dot means I'm never done. I'm never done with this problem. I anti-differentiate term by term, and there's infinitely many terms, so I'm still anti-differentiating, and I never get done with the problem. So maybe the answer is you can't do it. Or maybe the answer is this integral, when I take it, gets closer and closer and closer to a function that describes the area under that function. In other words, it's a limit problem. And we're going to have to look at the details of this. Can I anti-differentiate term by term? Well, the integral of the sum is the sum of the integrals. So it works if I cover up the dot, 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 I can do this one. So it seems reasonable that I might be able to do it with the dot, dot, dot. And of course, the proof of that is coming later. We're just going to experiment with it and see if it gives us something that seems nice. All right, so how do you do this? Anti-differentiate term by term. So what do I get? Integral of 1.
X.
X. Integral of x, x squared.
1/3, negative 1/3 x cubed.
Okay, beautiful. Next one. Plus 1/5 x to the 5th.
Yeah.
Okay. Minus 1/7 x to the 7th, right? Plus 1/9 x to the 9th, right? Minus dot, dot, dot. And what do you get at the very end? At the very, very end. We always add a what?
Plus C.
1.
Yeah, oh, plus C, yeah. And I'm going to put it up here in the front because that's the constant. Okay, so what I'm claiming is that if we can get our heads wrapped around this, and if this is true, then we should be able to anti-differentiate term by term, and we would be able to anti-differentiate a power series and get another power series. This is beautiful. Okay, so what? So I get another power series. Well, so what power series is this? Do you recognize it? Which one is that?
Oh, that.
Oh yeah, you got to
So
go to your list
1
of,
over x plus 1,
I got to memorize them all. You're close,
1 plus x.
close. Unless I wrote the wrong one down. Let's hope I didn't.
Oh,
That's,
it's 1 plus x squared.
yeah.
1 plus x squared. Okay. Well, wait a minute. Don't you guys know an integral of 1 over 1 plus x squared?
Yeah.
What is it?
Okay. That's integral of. That's
The arctangent?
yeah.
It is.
Oh my gosh. I knew that was gonna come.
Oh, wow. This is all of a sudden like this right here. Most amazing thing in like all of mathematics. I don't know, for me, I don't know. It's really cool. I love this.
Wait, I have a question.
Mm-hmm.
Oh, never mind. I'm dumb. Sorry.
Okay.
Continue.
Notice that you get a plus C on this side, and that plus C and this plus C would be a plus C, and I'm going to move it over to this side, just have 1 plus C. All right, so that's fine. But is this really true? Let's go see. Right? Of course, we've got a problem with the interval of convergence and all that kind of good stuff. In fact, you could tell me what it is before I share my screen. Maybe I can't get out of this now. Okay, so what is the interval of convergence for this guy?
Should be -1 to 1.
-1 to 1. And so if it works the same way as derivatives, then it turns out that the radius of convergence for the integral is going to be the same as the radius of convergence for the function or for the power series. So we're expecting this would only work on -1 to 1. Okay, but let's go look anyway. Okay, so here we go. Oh, this is so cool. This is so cool. All right, since we found this, the series first, I'm going to write the series down first. So what would I write? I'd write x minus, I'd write x minus 1/3 x cubed. Notice that the c just slides it up and down. And so I really don't have to add it in here unless I need to, slide it up and down. X to the 5th. Okay, this is looking beautiful. Minus 1/7, right? Minus 1/7, x to the 7th. I'm kind of thinking though, I don't want to keep on going like this forever, writing terms down. Instead, I'd really like to write it in summation notation. So one of the skills that you guys should be working on is, I give you one like this, you write it in summation notation because it's way easier to put it in Desmos in that form. So how about that? Can we do that? How do I write this as a sum? And you can leave the C off if you want. You could say C equals 0. That's fine. N equals, I'm going to get the powers first. The powers go 1, 3, 5, 7, 9, yeah? So I'm going to start at n equals 1, go to infinity, and write x to the what? I'm going to
It's
start
n
at,
minus 1.
I'm going to start at, did I mess up? Oh, n minus 1, is that what you wanted? N minus
Yeah, I
1.
think so.
N minus 1, that doesn't look so good. Because if I stick in 1, I got x to the 0, I wanted 1. And if I stick in 2, I've got 2 minus 1, which is 1, and I got to get to 3.
Should be n plus 1.
And plus 1 should be more than that.
So when you take
Hmm.
the derivative or the antiderivative, you change it from n equals 0 to n equals 1?
Maybe,
Oh.
maybe, right? But all we're doing right now is just trying to write this
Hmm.
in summation notation. That's it.
Okay.
So I'm not thinking about like what's going on with the index,
it's-
the derivative, or the integral at this point, but there is something going on. Okay, I just want to turn this into summation notation, that's all.
It's 1 over n plus 1 times x to the n plus 1.
N plus 1.
And then
Well,
that's going
I
to be,
agree with this. I'm
Hmm.
agreeing that there's definitely something in the bottom down here, right? And you're telling me it's like n plus 1, but I don't believe you. You were telling me it's something like this, but I don't believe you. Because when I put in n equals 2, right? N equals
Yeah.
2. Let's see, I get 3. But when I put n equals 3, I get 4. And the next one's not 4. The next one's 5.
Mm.
So try again. How do I produce the odd numbers?
Oh,
That's
wait.
what I got in the powers, don't I?
1 over 2n
Okay,
minus
some
1
2n plus 1.
minus,
Let's see, if I start at 1, then this would start at 3, yeah?
yeah.
Okay, so I
Yeah,
could make this minus 1, and then I would start at 1. Or I could have started at 0 and used 2n plus 1. All right, tell me about the power on the x. Same? These are the same numbers, right? Bottom and top.
No, yeah,
Yeah.
2 minus 1.
So 2n minus 1. Okay, and
And
you're
then
real close, except all these terms are positive, and these terms are doing what?
flipping,
We're
so
alternating.
Alternating. So I need a minus 1 to the
to the nth power.
close.
Oh, to
To
the 2n minus 1 power? No, hold on.
Nope, because those would all be odd. That'd make them all negative.
Yeah, but when it's squared, it's negative, so that's kind of
Right? So we want to start with a positive one, don't we?
Mm-hmm.
So we want to start with a positive one. So if I start with a 1 up here, if I put an n up here and start with the 1, it'll start with a negative.
So would you make that n plus 1? Would you make it
N plus 1 would do it.
yeah,
What else could you
plus
do?
1?
You could do n minus 1. That would also work.
Yeah, yeah.
Can you see how this is going to be annoying for your teacher at this point?
Well,
Right? Because there's a
one,
lot of choices here, weren't there? I mean, we could have made this minus 1 or plus 1. We could have started at 0, and then this could have been plus. So there are a lot of choices to get this thing to come out the right way, depending on where you start and how you work it out. But I think this is it.
okay, yeah.
Okay. Now, I know that in the book, he likes to start at 0 a lot. So if we would have started at 0, then what will we get? Then we would get minus 1 to the n, right? Look, this is 1 smaller. So this is 1 smaller. So this is 1 smaller. Uh-oh. How do I get 1 smaller than that? 2n plus 1, yeah, over x to the 2n plus 1. Now I think we could write it that way as well. Which one's right? They're both right. Which one is WebAssign going to take? I have no idea. If it doesn't take them both, then you're going to have to change it to a different form. Okay, I would think it would probably take both. Now we started at 0 and 1. Could we have started at 6? And the answer is yes. You could have changed it around to start at the index being 6. But if you start at 6, WebAssign is definitely not going to take the one that starts at 6. Okay, so it probably takes the one that starts at 0 or 1. Now the question is, are we right? And the answer is, I don't know, but it's sure easier to type into Desmos at this point, because in Desmos, I can now type, instead of typing it like a polynomial just straight up, I can type it as a sum, and then I can let my my index, do you want to start at 0 or 1? We started at 1, so I'll do the 1. 1 to m. I like this m. This was a good decision, right? Because it defaults to n, and I kept messing that up and changing it to i's. So I like this better. Okay, minus 1 to the, and we want n plus 1 power. So we want 1, and I'm going to back up and go n plus. And then we want that whole thing divided by, what do we got? 2n minus 1. And then we've got x to the, I'm going to put a 1, and I'm going to back up and go 2n minus 1. Oh, I'm all the way to 100. Let's start with a flat one. There it is. There's 0. It's just flat. And there's 1. There's the line. And there's the 4th degree, 5th, 6th, 7th, 8th, 9th, 10th, 11th. Are you with me? Let's stop at about 30. You're trying to tell me that this little piece, and it looks like it's kind of doing its thing between -1 and 1, which we already talked about a little bit. This is supposed to be the same as what function?
Inverse tangent of x.
Inverse tangent of x. Oh, this is going to be the coolest thing ever. Ready? Oh, baby. Look at that. This is amazing because how do I find this? How do I find this number? What does that even mean? What is f of 1?
F of 1.
Yeah, what is that? That's the arctan of 1. That's a what?
Oh wait, that's
So that should be, what, pi over 4?
Yes, it should be. So that number should be pi over 4, which is good because it is pi over 4. It's an angle. It's an angle whose tangent is 1. So if you're having trouble kind of seeing that, then in the tiny little picture on the side, you go, oh, here's tangent right here. It's 1 long, right there. And that's the angle right there. And that's pi over 4. Do you remember this? Maybe that's too tiny. Okay, so what I'm saying is P of 1 should be pretty much the same thing. How come it's off a little bit? Well, look, where it only agrees between -1 and 1. It agrees really well between -1 and 1. Do we agree? But
Yeah.
over here at 1, it's starting to, oh, it's starting to go away. It's not agreeing so well. So maybe finding inverse tan of 1 using this process is not so good. But what if I found the inverse tangent of a half? What's that? Well, okay, back over here in our little picture, it's where I'll make, oops, I'm gonna make another picture somewhere. Okay, so we're trying to find an angle whose tangent is a half. So that's 1 tall, right? Because it's a unit circle. So a half is right about there. So now this is 1/2. And so the question is, what's this angle? Yeah? Is that too small? Can you see it? I'll switch over real quick. Right? That's what we're trying to find, right? We say the tangent is 1/2. I want to know the angle whose tangent is 1/2. So then let's go look. According to Desmos, it's 0.46367 something, yeah?
mm-hmm.
But how on earth does Desmos know this number? Okay, it's not pi over 4, right? I'm pretty sure it's not even pi over 8, right? It's not like if I make the angle half as big, the tangent's half as big. But what I'm going to claim is that this polynomial is giving you a pretty good approximation to it at the 30th power, right? With 30 terms, we're getting it pretty good, aren't we? In fact, it's right on to 11 decimal places. In fact, we don't even need a polynomial that's that big. This one still gives it pretty accurately. 4, 6, 3, 6, 4, 7. So there you go. There's 6 decimal places of accuracy. So the question is, how on earth does Desmos know the arctangent? That's a very good question. And I
That
think
series we just,
it does the series that we just did. Okay, let me ask another question from Trig. And then we're going to have to stop. We could just keep going all day because this is so much fun, but we're going to have to stop anyway. Let me ask you
What is
this
it?
question. Okay. This is a really old story. Here it comes. We've already done a little bit of this story a couple of times. What's that length? And you say what?
1.
The
One,
radius.
yeah, we know that one, right? We know that length is 1. So what if I go 45 degrees here? Better known pi over 4, yeah?
Mm-hmm.
What's that length right there?
1.
1? No, this is 1.
Oh, sorry.
that length on
2 over
top.
2.
Did I hear it? I think I did.
That's root 2 over 2.
That is root 2 over 2. How do you know that? Come on, no one believes you. How do you know that?
The Pythagorean theorem.
Yes, it is. Maybe if I just draw the triangle right down here, right? This, and maybe if I use 45 instead of pi over 4 because it's a little bit easier, it's more familiar. Then this one's what?
Mm-hmm.
Pounds
All the
45.
angles have to add up to 180, don't they?
Yep.
At least in Euclid's universe. Okay, so however long this is, we don't know. So let's call it like x, yeah? Well, then how long is this?
That's also X.
That's also x because this thing is half of a square.
Mhm.
How long's this?
1.
1.
That's 1. So Pythagorean theorem says x squared plus x squared equals 1 squared.
Mhm.
That's 2x squared equals 1 squared. That means x squared equals a half. That means x equals, right, the square root of 1/2, which is the square root of 1 over the square root of 2, which is 1 over the square root of 2 multiplied by root 2 over root 2, which is equal to 1 times root 2 is 2, and root 2 times root 2 is also 2. Sorry, I ran off the page. Root 2 over 2? How are we doing? Pretty good? I'm feeling really good about that. Euclid would be so proud of us. Okay, you ready? Here comes another one. We're almost to the punchline. What if I turn 60 degrees? How long is that?
Believe that's.
That should be root 3 over 2, right?
Yes,
Yeah.
it is.
Mhm.
Mm-hmm.
That's root 3 over 2. How come? Starts with a P. Gloria already told you once.
Pythagorean theorem.
That's exactly right. It's a little more work now, though. This is 1, right? But if I draw this down here, then this is 1, right? This is 1, that's the radius. And so how long is this?
Wait.
I think it's root 3, isn't it?
Nope, this length right here, this one.
Is it also 1?
That's also 1. Because check it out. If this is 60, this is 60, making this one how much? 60, 60, 60, 60, equilateral, all the same. So do you know when I cut straight down what that does to the base? Cuts it in
Half.
half. So if I draw my picture down here now, I got 60 degrees and 30 degrees and 1/2. And this is 1. So how long is this? I don't know. Pythagorean theorem. Ready? Here it comes real fast because we're running out of time. X squared plus half squared would have to be equal to 1 squared. So x squared would equal 3/4. I'm in a hurry now. Yeah, 1 minus a quarter, half squared is a quarter, 1 minus a quarter, 3/4 square root.
Yep.
Would be square root of 3 over 2. And my thing's not focusing. All right. This is awesome. Pythagoras and Euclid are so happy. Okay, but now check this out. Are you ready? Here comes the hard part. Oh boy. Oh, you're not going to like this. Ready? 40 degrees. How long's this? Oh, I'll do the other one. We did 60 degrees and we did 45 degrees. So let's go right in here. How long's this? 50 degrees. And you say, I don't know, but it's somewhere in between what?
60 and 45.
I'm thinking it's somewhere between root 2 over 2 and root 3 over 2.
Mm-hmm.
Yep. But I want to know exactly how long it is. So tell me one way you could find it.
Use an inverse trig.
Ooh, not even have to do an inverse trig. Do you remember the name of this length? We call this length the what? It's related to this length.
Sine.
This length is called the sine of the angle. So I'm saying that this length right here is the sine of 50.
Mm-hmm.
It is the sine of 50, meaning whatever number that is, that's how long that is. So the exact value for that length is the sine of 50. But I don't know what it is. I just know it's between root 2 over 2 and root 3 over 2. There's no trick using geometry to be able to find it. So check this out. Bam, 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 boom, new, that was pretty cool. Okay, sine, I don't know what this is gonna freak out now. How come it says that the sine is negative length, negative 0.26?
Isn't it doing radians?
Yeah, it's doing radians. It defaults to radians. So now if you want to change it, you'd have to go over here and you'd have to say, put it in degrees. Okay, now that looks good. It's about 0.766. That should be somewhere between square root 3 over 2, right? And square root 3, not square root 3 halves. Square root 3 over 2 and square root 2 over 2, yeah? Whoops. Looks good. It's in between there. That's good. So it looks like maybe Desmos is telling us the right number. How does it know that that's the right number? In fact, we've been taking the sine of angles for a really long time now. Some of you guys since like kindergarten. And you've been just writing down what their values are. How do we know that the values are what we say they are? Well, you're going to have to wait now till Friday, I guess, to find out. You know? I'm thinking there's something very special going on here. And that is that it's really hard to find some values of these functions, right? We can approximate them, but to get them exactly is getting to be a little tricky. You say, well, I just push it on my calculator and my calculator gives me the number. But now we got to go a little deeper. We got to say, well, how does the calculator know what number to give you? Right? What is the calculator doing to give you that number? And that's what we'd like to explore in a little bit more detail. So in the meantime, though, you keep playing the game, right? So what did we do? Here's the recap. The recap is you've started to build some of these power series for different functions. And you're getting a list of ones that you have memorized. Right? We've got 5 of them on the list now, because I think inverse tangent's interesting enough. You should memorize that one too. So now I want to give you a new function and have you find a power series for it. And the trick was, maybe if I can make the function, the new one, look kind of like the old one with some algebra, then I could do a substitution. But then toward the end, we ended up with 2 new tricks. And that was, well, maybe I could take the derivative or the integral of one of my power series to get a new power series that's equal to a new function. I would challenge you to look at this one more time. This is one of our favorites, right? What would I get? What would I get if I did this? Certainly this side's doable. It's just the power rule, isn't it? Just do the power rule and go backwards. Okay, beautiful. You can do this side. As long as we can deal with the dot, 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 which we're going to ignore for now. All right, so now tell me about this side. What's that?
Isn't that going to be like the natural log?
Yeah, the negative natural log of 1 minus x.
Well, that's kind of cool because I'm kind of thinking a lot like inverse tangent. Finding values of the natural log function, not fun, right?
Yeah.
But what if we had a power series and all we had to do was plug in numbers to the power series and we got the same values? We got the values for the natural log by using a polynomial instead. Boy, that'd be way easier.
That's
Now I think we're heading down the right road. So you play with a few more of these. See if you can build a few more. And then you know what question we're going to ask. Okay, we got a natural log. We got an inverse tangent. So what's the next question? Is there a power series, right? Is there a power series for this, right? Cn x to the n, yeah? Is there a power series can I find coefficient C so that I can write the sign as a power series? Because if I could, then I could approximate all the values of the sine x using my power series, which is super easy because a power series is just a polynomial. And then if I'm Desmos, I don't need to worry about the dot, dot, dot. I just go over far enough that I got 11 decimal places of accuracy and I just call it good. And most of us, okay, are pretty happy with 11 decimal places of accuracy. So that usually satisfies most of us it satisfies everybody that's not a mathematician. Okay, because if you're an engineer and you engineer something to 11 decimal places of accuracy, it's close enough. Okay? Now, there's still some mathematical concerns about what happens with the dot, 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 right? But let's see if we can solve this problem, because that would really make our life a lot easier. And that's what I'd like to do on Friday. Okay, oh my goodness. So we're way out of time because my thing's already binging at me that I'm supposed to be at office hours. So I am going to let you go. You try a few of these. In the homework. Be aware that because the index can start and stop at a different place, sometimes WebAssign's a little finicky about it. Okay, so sometimes you have to change the form around and it doesn't take the exact form that you came up with. But for the most part, I think you should be able to get most of these. Okay, is that enough for today?
Yeah, one last question I had looking at some of the answers we had earlier to some of our problems.
Okay.
Is the antiderivative of the sum of the antiderivative?
The antiderivative, the integral of the sum of two functions, right, is
Oh no,
certainly,
of the summation.
The integral of the summation. Well, this is certainly true, right? This is the integral of this plus, I need a dx, and the integral of this. This for sure is true. And we're going to take on faith that I can anti-differentiate an infinite sum the same way. I can do it term by term. So yes is the answer to your question.
So
we haven't really proved it yet, but we're going to take it on faith for now.
So you can take the antiderivative from outside the summation and put it inside on the function inside and get the answer.
Yes, you can. Pretty cool, huh? Now, I might say, okay, that only works when it works. There are some functions for which it doesn't work. And certainly the function would have to exist for anything to work. So you got to be a little bit careful about holes and jumps and discontinuities. you got to be a little bit, yes, there's a whole bunch of graduate level math that you can do to prove when it's possible to put the integral inside the sum and the sum inside the integral and switch them like that. And the answer is it's going to work for all the ones that we're going to see, but it doesn't always work. There are some details about that we can worry about later. So the answer to your question is still yes.
All right.
Okay. All right. That's all I got. We got to go. So you try a few of these, and then I'm going to see you guys on Friday, and we'll try to figure out, is there a power series for the sine? And if we can get the sine, then what about the cosine and the tangent and the e to the x and log x and all these other functions that we've been so happy to deal with for so long? That's going to be our plan. Curtis.
Just real quick, just so that I'm on the same page. Are we beyond 11.8, moving on to 8.9?
This is 11.9.
Okay.
In fact, this is the end of 11.9. Okay, I think 11.8 was just really dealing with interval of convergence and where it converges and doesn't. And 11.9 was representing functions. So that's what we've been doing. We've been trying to represent functions using a power series. Okay. All right. I will see you guys on Friday. Have a great couple of days. Stay safe,
thanks.
stay healthy.
See you then.
Okay, see you.
Bye.